Hello, everyone. Welcome back to CPE EE 517-WS Digital and Computer System Architecture. This is part 4 of lecture 9. We're going to do GPU programming tutorial. This is the device outline of one processing units of GPU. That's called streaming processor, or SMX. In this streaming processor, you have the instruction cache to cache the instructions, and then instruction buffer, and then SIMD thread scheduler, and then dispatch units to dispatch them on different GPU cores, double floating point unit, load store unit, special function unit. And then you have the L1 cache, and then share memory, and then off-chip F2 memory. So you can see here, this is how typically we have like 20 to 80 this kind of processors. Taking them together, it's around thousands of GPU cores. Okay. How does GPU programming work? The thing you want to keep in mind is that GPU is like a puppy of CPU. Okay. You have to use CPU to run, to invoke GPU, and then GPU can do the job. Okay, so this is a Vim editor we used for programming. So for Vim editor, we have 4 modes: normal, insert, command, and virtual modes. For those of you who knows Vim editor, you can fast forward, go to next slide. Okay. When you start with Vim, it is in normal mode, like Vim path to file. You would undo your previous change. Control R would redo. When you type IAAOO from normal mode, you enter insertion mode, insert mode. When you insert mode, you can edit the contents of the file. From a normal mode, you type semicolon. Okay. We'll transit you to command mode. In command mode, you can save and you can exit the current file. For example, if it's a semicolon W, you save the change. Sorry, it's not semicolon, it's colon, right? It's colon. Okay, the colon symbol here. When you do colon W, it saves the change. Colon Q, quit the file. Colon Q, asterisk. I'm sorry, I'm really bad at the symbols. So this is a colon and this exclamation, right? So colon Q exclamation, you quit without saving. In virtual mode, when you type V for normal mode, you can select copy paste text from virtual mode. You can put a .vimrc file in your home folder to help you syntax your program, like highlighting, like coloring, etc. So you can see for Vim editor, you typically start with the normal mode, and then you can transit to insert mode, and then you can do ESC. ESC, then you go to normal mode again, and then you do colon, you enter comma, command mode, and then in normal mode, you type V, you enter virtual mode. Okay. Okay, so the third review is about the C++ programming. So assuming we do vector addition, we program the, we first allocate the arrays of A, B, C, and then we randomize the value or initialization for A and B, and then we call the vector add function. Finally, we output the results, right? So the vector add function is the kernel function that performs the vector addition. After we do this, we save the file. For example, if we save it to vec_adder.cpp, then what we do next is we compile this file to another executable. when we do execution, we basically do dot x vec underscore adder, right? Excuse me. So when you are doing GPU programming, you first have to identify where is the parallelizable part of your program, right? In this case, you figure out that probably vector addition is the parallelizable part. And then the main function is the sequential part. So what you do is you parallelize this parallelizable part on GPU and perform the sequential part or serial part on CPU. How it works is like this. In GPU programming convention, you first allocate data on device memory here. Right here, step 1. And then you copy the data from the CPU DRAM to GPU, right? You copy them from CPU to GPU. And then you launch the kernel that works on GPU. That's a vector addition. After it's finished, you copy the result from GPU to CPU back to CPU. And then you free the device memory, right? That's how the 5 steps works, okay? So then we're gonna discuss how these 5 steps are done on GPU. First, we have to allocate memory on GPU. So what we do is, since we have to call on CPU, then what we do is we basically do a C runtime malloc, right? In C, we do int a, and then we malloc the address in CPU, and then check if a is a null pointer. If it is not, that means we successfully get the result, get the space. Well, for GPU-based allocation, since we call this CUDA malloc on CPU, and it works for the device, so what we do is we pass this one as a parameter to the CUDA malloc, okay? And then the CUDA malloc gonna malloc this space, and if a underscore d is not null, then that means we're correct. For the last part of step 5, what we do in C is we free a. Well, in CUDA, we do CUDA free a underscore d. So the problem here is why we pass the pointer to pointer of a underscore d to CUDA malloc instead of we just find the pass the pointer of a underscore d. This is not related to any GPU specific case. It's really just a pass by reference. What you can do here is, assuming you have implemented the CUDA malloc by yourself, you implement your own malloc function here like this. So if you pass a in my alloc as a pointer instead of pointer to pointer, what you get is the return value of a will not be passed back to a because it's passed by value of the a, right? So the value of the pointer wouldn't work. So what we do here typically is we have to really malloc we have to pass in the pointer to that specific pointer, right? This won't work. Do this, it will be a segmentation fault. Segmentation fault. The reason is that you pass the value of a to malloc, but you change in this line, you change the value of a. However, since it's passed by value, this will not affect the original value outside of this function, right? Outside of this malloc, like in this line. Even you change the a inside of this kernel, but it's not affecting the outside part, okay? Step 2 to step 4, we copy data between host and device. So we're gonna present in the same way as what we did before. So in C runtime memory, what we do is we do memory copy. Well, in CUDA-based memory copy, what we do is similar, right? We still do device, source, count, but we have to include one more enumeration type. That is, how do we do memory copy? Either we want to copy from GPU to GPU, or CPU to GPU, or GPU to CPU, right? So there are 4 parts of copying case, like host to host, host to host. That means in CPU. Host to device means from CPU to GPU. Device to host means from GPU to CPU, and device to device means from GPU to GPU, right? Then the third part is probably the most challenging part to understand it, is the GPU thread organization, right? Assuming we have the GPUs, we have to first understand how do we actually organize the threads on GPU. So we organize that in a hierarchical way. First is we have in total all the threads, we call it a grid. And then inside of the grid, we partition them into blocks, okay? Several blocks. And then inside of the blocks, all the threads are in each block. So what do we do? Since we partition them into blocks, so every block has its unique block ID. And inside of the block, every thread has its own unique ID inside of the block. So by saying that, it also implies that in block 0, you have thread 0. In block 1, you also have thread 0. So we cannot just use the thread ID in the block to uniquely identify the threads across the entire grid, or basically across all the threads. We basically have to use the block ID, it's like the group ID, plus as well as what is the thread's ID inside of this group together to decide the unique ID of this thread, right? For instance, here, if we have like in total 3 groups, every group has in total 4 threads. So what we do is we have the thread ID in the block as 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And the block ID are 0, 1, 2, right? So how do we calculate the thread ID of this one across all the groups? Okay. It would be good if you guys can pause the video for 5 minutes to calculate the unique ID of these threads across all the blocks. Okay. All right. So coming back, so the case is we first have to figure out the size of the block, right? The size of the block is the block dim.x, and then the block ID. Multiply the block ID. So it's block IDX dot x. Together, this tells you what's the offset of the threads in this block. And then it plus the thread ID in the block, right? Is the exact ID across the thread, across the entire grid. Okay. So that is how we calculate the thread ID across the entire grid. So we use the block ID, multiply the block size plus thread ID. Let's do a verification. For instance, if we want to figure out this thread's ID, so what we do is 1 multiply 4, right? So it's a 4 plus its ID is 1. So in total, we say this is the 5th. The ID is 5. 0, 1, 2, 3, 4, 5, right? So for this one, we can do another verification, right? For this one, the block ID is 2. Multiply the size of the block is 8, right? 8 plus 2 equals 10. let's count whether it's 10 threads, okay? From 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So exactly. So that means we use the block ID multiply the block dim plus the thread ID X. Exactly tells us what's the offset of this thread across the entire grid. Okay, so the next problem for us is when can we finish? When can each thread decide it's a time for itself to quit? And after it finishes the 10th index, what's the next index should this thread work on? Okay. If you can pause your video for 5 minutes and think about this problem, try to solve it, that'll be good. Okay. All right. Okay. So please use 5 minutes to solve these two problems. Okay. And then let's show you how to solve these two problems. See here, if we block 0, it moves by the entire total size, right? So for example, for thread 0, it comes from 0 index to 12, thread 1 from 1 to 13, thread 2 from 2 to 14. So it's all of them moving by like 12, the total number of threads, basically, right? Similarly for this one, from 4 to 16, from 5 to 17. For this one, same, from 8 to 20, 9 to 21, 10 to 22, 11 to 23. So the TID, this offset is the size, the total number of threads in this grid. That is number of blocks multiply the block size, right? Number of blocks is a grid dim size, dim X, and the size of the block is block dim dot X. Okay. Then when will we quit? Whenever every thread, its TID goes beyond the length, right? Let's see. So once this one goes to 12, what's the next? If you add by 12, it's 24. It exactly goes beyond the index. Similarly for 13, goes beyond 14, goes beyond 15, goes beyond. So that means when the TID goes beyond the length of the vector, it's the time for us to stop. Okay. So putting them together, it becomes from the vector add of AI, BI to CI, it becomes first we calculate the thread ID, and then we use this thread ID to index the data. So that is thread centric. That's what we mentioned before, right? So the thread use its thread ID to find out its own data, and then this thread gonna be centered on its own vision to finish its own computation. So that's why we say it's thread centric. So typically for the thread descriptors, we have 3-dimensional descriptors, not only X, but also Y and Z. Block, similarly Y and Z, block dim X, Y, Z, grid dim Y, Z, and function descriptor. We have underscore, underscore, global, underscore, 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 device, underscore, underscore, and host. We have synchronization descriptors, memory descriptors, communication descriptors. Okay. For multi-dimensional thread organization, it's pretty good for figure implementation because think about it, it's like a 2-dimensional data, right? So we use both X and Y. And then putting them together, we have this function, right? So we have this serialized CPU version of allocating the data on CPU, initialize the data, and then allocates the device data, copy data from the CPU to the GPU, right? CPU to GPU. And then we'll call the kernel, and then we'll copy the result back to the CPU. That's it. So here we also have the config, the size of the number of the blocks and the size of the block, right? This can also be done exactly by like programmers, right? So you can typically what we do is we set this as 128 and 128 or 256 and 256. It's typically like that. Don't go like not 2 to n, right? So it should be 2 to n. So for kernel launch, this is the thing, right? We can either choose the data number of data entries equals the number of blocks multiply number of threads, or we can always use a decided number of blocks and decided number of threads in the block. Which one's better? Typically, we say this one's better because we can reuse the threads for more workload versus we create too many threads. It's like we create a lot of people who are crowded to enter all the situations, right? So once we have this GPU program implemented, what we're gonna do is we're gonna like what we did in GCC or G++, we do compilation in terminal. So here, the compiler is NVCC, okay, like this. You NVCC this file and put it in executable and then execute this executable. So for compiling the CUDA source code, we do this kind of, we have compiler and then we compile C, we compare the kernel and then we do heterogeneous computation, right? For GPU, people might also be interested in saying what's the property of different parameters like CUDA device property. We can get a device name, multiprocessor count, register per block, total global memory, max threads per block. And also, it's also very popular that in today's supercomputers, your nodes might have more than one device, right? One GPU. So how do you select which device to work on? You can use CUDA device, set device. And when you are doing coding, it's very, very important for us to handle errors. Why? Because GPU is like black box. You don't know where the error happens. It's better you check the output of all the errors so that you understand, oh, this kernel has a problem. Then it narrows down your scope of debugging, right? For programmers, you know, we want all programmers, we know that 90% of our efforts go to debugging, right? So this is what I provided as error handler. Okay. So our program is to basically show how it works and then debugging, etc. So what I'm gonna do is I'm gonna show you how it works. Okay, so now it works, right? So we can see here. What I do is I use this kernel function to do vector addition, and then I copy the result back from CP device to C, and then we assert whether it works, right? If it works, then you're gonna printf succeed. Otherwise, it's gonna be failed due to assert. Right? Okay. Okay, so I think that's it for this lecture. I'm gonna upload both the video as well as the source code. Let me know if you guys have any questions.